Hello, my name's Dr. AJ Kumar, PhD. I'm the smartest mathematician who ever lived. I'm the founder of QAnal, and I'm also doing this playlist, Math for Programmers. This is number 3, which is reducing fractions, and we're going to look at some code in Erlang and some code in Rust, and look at the difference. And there's a photograph of me, obviously. So last time I told you that what I'm going to have to do in this video, number 1, so context here, we're talking about reducing fractions, and so the way we're storing them as pairs of integers, and we have to have something called a reduction procedure. So basic problem, there's many different pairs of integers which will correspond to the same fraction. And we want to reduce, if we have two things that are equal, we want to store them using identical representations. Equal things have identical representations. And so that implies, because we're insisting on computability, we have to have a reduction rule. So we have to, in addition to having a canonical form, so the way that canonical means sort of given, I guess. So we have to have a way to reduce fractions, basically. And I told you that the way to do that is to, number 1, pick a sign convention. So we picked that the bottom of the fraction has to be strictly positive, and and then I said that in order to cancel all the common factors between the top and the bottom of the fraction, instead of factoring the top and the bottom and canceling the common factors, instead what we're going to do is just calculate the GCD. Factoring is really slow, finding the GCD is really fast, and then divide both the top and the bottom by the GCD, and that'll cancel all the common factors. And so I had to convince you of that, and that rests on fact star, which is any common divisor of two integers divides their GCD. And I'm going to half convince you in this video, but really what I want to do is explain the Euclidean algorithm and show you some code and show you how we actually use this, and then go back to how is this supposed to actually work. And I want to repeat the warning: Erlang will permanently change the way you think about reality. Don't say I didn't warn you. Alright, so like I said, today we're doing 2 and 3 and kind of 1. And we got to circle back to 1 and do it a little bit differently. And I'm going to give you half the argument for 1 today and show you that really the argument for 1, you have to be careful to not make a circular argument, but it requires that you understand how the Euclidean algorithm works. Alright, so given that I'm not going to convince you that it is the GCD, which is kind of, okay, let's just get, okay. There's a proper frame of reference for today in order to avoid, we're in danger of kind of making a circular argument. So what I want you to do is, instead of GCD, I'm going to just compute this number. It is the GCD, but we're going to call it the Euclid number of the two integers, and that's to avoid worrying about the semantic meaning of greatest common divisor for a moment. It'll be obvious from our construction. So given two numbers a and b, integers a and b, we're computing a statistic called their Euclid number. Statistic means computable function of the data. It means measurable function of the data, but measure theory is some CIA bullshit. So think computable function of the data. It'll be obvious that the Euclid number is a common divisor of the two integers. Next time we'll prove the starred fact, which is any common divisor of two integers divides the Euclid number, and I'm going to outline that argument today. Therefore, glowy green, with respect to the divisibility ordering on the integers, ordering as a reserve term, the Euclid number of two integers a and b is the greatest lower bound. Now I've got a graph over here to show you, but thus it is reasonable to call the Euclid number the greatest common divisor. So accept this on faith for now. The dual concept, which is the least upper bound, so the greatest lower bound is the greatest common divisor. The least upper bound, which is sort of the dual concept, is called the least common multiple. Right, we have to be careful to avoid a circular argument, which is why I'm calling it the Euclid number and not the greatest common divisor right now. So let's look at some examples, and then we'll look at some code. So over here, say I want to reduce 60 divided by 105. And the reduced form of that fraction is 4/7. So if we are naive, we factor 60 into 2 times 2 times 3 times 5, factor it into prime numbers, I mean. And then 105 is 3 times 5 times 7, I hope. I factored that in my head. I may have gotten that wrong. I think that's right. Anyway, we cancel the common factors, and that's 2 times 2 over 7, or 4 divided by 7, and there's no common factors. And when two numbers have no common factors, they're called coprime or relatively prime. Okay, and now if we look at this thing, this is called the divisibility graph, or the divisibility network. I think it's a special kind of graph. I think it's called a Hasse diagram. I'm not super up to date on my graph theory jargon, so forgive me. But let's just, this is a subgraph of the divisibility graph. The entire divisibility graph is infinite. It's also a directed graph, which means that well, it means that the edges, so graph has nodes and edges, and a directed graph is when the edges are one-way streets. So this, if you have a Hasse diagram, you also have what's called a partial ordering. So you're familiar with a normal ordering, so like 1 is less than or equal to 2, that's a normal ordering. The difference between a normal ordering or a complete ordering, what's it called? A total ordering, that's the word. The difference between a total ordering and a partial ordering is sometimes in a partial ordering you have two things that are not comparable. So for instance, it's not, with respect to the divisibility relation, it's not true that 5 is less than or equal to 7 or that 7 is less than or equal to 5. So the reason this is glowy green is because we're playing word games with the word greatest. It means greatest with respect to the divisibility ordering. So I just want to zoom out for a moment. Just look at 1 and look at 0. Okay. The reason this is glowy terminology, 1 divides everything, so everything is divisible by 1. 0 is divisible by everything, so 1 divides everything and nothing divides 1. So 1 is a universal lower bound. 0 is a universal upper bound. So everything divides 0 and 0 divides nothing. So if I draw this kind of subset of the graph, so not all of the edges are shown. So for instance, there should be an edge from 3 to 60, but I'm not showing everyone because there's too many and I don't want to clutter the graph. It's already cluttered enough. So if we have 60 and 105, what the GCD is, it is the biggest element, it's the biggest node, biggest with respect to the graph theory relationship, with respect to the partial ordering. It is the biggest node that is a lower bound of both 60 and 105. The opposite is the LCM, which is the smallest node that is an upper bound of both 60 and 105. Also, if you have, for instance, 4 and 2, then the GCD is 2. So lower bound doesn't have to be a strict lower bound. Okay. Two integers are relatively prime if they're if the greatest lower bound between them is 1, which is the universal lower bound, which would also imply does that imply their LCM is 0? No, it does not, because then their LCM would be their product. Sorry about that. That's not. So they're not quite 100% dual, because you don't have the complete duality between the... No. Anyway, but 0 is a universal upper bound, 1 is a universal lower bound. The prime numbers are characterized by they're exactly one edge away from 1, which is kind of an interesting idea. Anyway, so if we have 60 and 105, their GCD is 15. And then if we kind of look at the ancestors of 60 and 105 that aren't related to, that don't include their GCD, we get 4 and 7, which are the top and bottom of the reduced fraction. Anyway, and then another weird fact is 60 times 105, that's their product, 6,300. The LCM times the GCD equals the product. It's an interesting quirk. Anyway, let's just look at some examples. And so first thing, in the context, so we want to divide 60, we want to reduce 60 divided by 105, and we want to nail down exactly how to do this. So in the context of eliminating, let me make sure I'm actually recording with the right microphone. Sometimes I don't. Okay. So In the context of eliminating common divisors, let's agree that all of these are the same problem. So all we're interested in is eliminating the common divisors. First thing is we don't care about signs, okay? So 60 and 105, 60 and a minus 105, minus 6, these are all the same problem in terms of eliminating common divisors. So that's what I mean by the negative numbers really play no essential role here. All we really care about is sort of the positive or non-negative part of the number, okay? And also, we don't care about the ordering. So the common divisor, the greatest common divisor of 60 and 105, or the Euclid number, I should say, is the same as the Euclid number of 105 and 60. All right, and so we have this principle that I stated last time, or maybe a couple times ago. Equivalent things should have identical representations. Well, there's kind of a generalization of that, which is that equivalent problems should have identical solutions. Or in other words, our strategy in both cases is to sort of pick one version of the problem, solve it, and then convert all the other equivalent problems to our already solved problem. And so that's why I circled number 5. This is the one we're going to solve. So we want the bigger number to be on the left, and we want them both to be non-negative. We don't want to worry about signs, okay? So that's what we're doing. So in this case, we're picking case 5. So here's our pseudocode procedure. So we want the Euclid number of A and B. So we're going to take the Euclid, we're going to call it Euclid abs. So we're going to pass the buck to another function, but we pass it the absolute value of A and the absolute value of B, and that eliminates any sign issues. Okay, what Euclid abs does is fixes the ordering and makes sure, and then passes the buck to Euclid plus. So if x is less than y, then because we want the left argument to be bigger than or equal to the right argument, then we do Euclid plus of yx, otherwise we do Euclid plus of xy. So if the ordering is wrong, swap the ordering, send it to Euclid plus, else do Euclid plus with the same ordering. And Euclid plus, well, how do we do that? Okay, let's go back to our example. Remember, our task is to reduce 60 divided by 105. So our strategy is to calculate E of 60 and 105, which is D. So this is our original problem. Our strategy, just to recall, we're going to calculate the Euclid number between 60 and 105, and then the result, the reduced fraction, will be 60 divided by D and 105 divided by D. And if you go up here, back to our example, if you notice, well, if we cancel the common factors, 3 times 5, that's 15, which is the GCD. And so 4 is 60 divided by 15, and 7 is 105 divided by 15. And so that's kind of where you get these two extremities on the edge of the division graph. Anyway, let's see. Yeah. So our result will be 60 divided by D and 105 divided by D. Okay. So we've established that the Euclid number between 60 and 105 is the same as the Euclid number of 105 and 60. So how do we calculate the Euclid number of 105 and 60? So we agreed that this is the version of the problem we want to solve. So our trick is to use division with remainder. Instead of having to factor, we're going to use division with remainder. So we're going to say 105 is 1 times 60 plus 45. Now 1 in this case is called the quotient. I wrote that it's unimportant in our story. It'll actually be important when we're proving fact star. So for now it's unimportant. It'll be important later. Our trick is to use division with remainder. So this is, if you've done programming, this is the integer division of, so 105 integer division by 60 is equal to 1. Okay? And this is called the quotient. So anytime you see something in brackets, that means it's a jargon term or reserved term. And 45 is the remainder. So 105% 60 in most languages. In Erlang, it's 105 rem 60. 105/60 in most languages gives you the quotient, the result of integer division. 105 div 60 in Erlang. And what this means, so the quotient is the result of integer division. The remainder is the remainder after doing integer division. And that they have the relationship 105 is equal to 1 times, so A is equal to the quotient times B plus the remainder. That's always true. Okay, if we rearrange this equation, so we have 105 is equal to 105 minus 1 times 60 is equal to 45. Well, now it's obviously true that any common divisor of 105 and 60 must also divide 45. So anything that divides both 105 and 60, divides means that when you, here's a way to think about it. A divides B precisely when the remainder of B divided by A is 0. That's a way to think about it, if you need a definition. So any common divisor of 105 and 60 must also divide 45. So if you imagine, let's say, okay, 3 is a common divisor of 105 and 60. So if we divide both sides of this equation by 3, we're going to get, what we'll get is integer minus integer must equal integer. Anything that divides any common divisor of 105 and 60 will certainly divide the left-hand side of this equation, and therefore anything that divides the left-hand side of the equation must also divide the right-hand side, which is just 45. So any common divisor of two numbers must also divide their remainder. Right. Generally, if A is greater than or equal to B, then any common divisor of A and B also divides their remainder of A and B. The remainder is an asymmetrical operator, so you have to be careful. It's not true that that A remainder B is equal to B remainder A. So if A is greater than or equal to B, then the Euclid number between A and B is equal, so the GCD between 105 and 60, another way to state this, any common divisor of 105 and 60 is also a common divisor of 60 and 45. That's the way to think about it. So if A is greater than or equal to B, then Euclid of AB is equal to Euclid of BR, where R is the remainder. And R, because we've fixed that sign nonsense and fixed the ordering, that's why this is important. R has the property that 0 is less than or equal to R, and R is less than or equal to, or R is strictly less than B. Right, note the strict inequality. So, right, if we got, let's say, blah is equal to something times 60 plus 61. So, what is 1 times 60 plus 61? So if instead we had 121 over here, we would have 121 equals 1 times 60 plus 61. In that case, it would be, the quotient properly would be 2. So instead you would write that as 121 is equal to 2 times 60 plus 1. So if you kind of overflow, then you increment the quotient, and then you can always get this R so that it is between 0 and B. And it could be 0, but it can never be as high as B. Okay. 0 is the universal upper bound in the divisibility graph. So the Euclid number of x with 0, doesn't matter what x is always going to be equal to x, which is our terminal case. So generally what we're going to be doing is just, when we get the Euclid number of A and B, we're going to take the Euclid number of B and R, where R is the remainder. And this is always just going to keep giving us a sequence of smaller and smaller numbers until we eventually get R is equal to 0. This is just recursion. This is how recursion works. So 0 is the universal upper bound in the divisibility. Right. So if we go back up here to our graph, if we keep doing this E of 60 and 105, we're eventually going to get to E of 15 and 0, in which case the answer is 15. So let me show you how this works. Okay. So in full, we want to reduce 60 divided by 105. So we call E of 60 105. This gives us E of 105 and 60, which is E of 60 and 45, because 45 is the remainder 105 divided by 60. Well, what's the remainder of 60 divided by 45 is 15. So 60 is equal to 1 times 45 plus 15. Well, 15 is equal, or 45 is equal to 3 times 15 plus 0, so the answer is 15. Right? Pause the video and convince yourself that this makes sense. Okay? So, 60 divided by 105, we reduce that to 60 divided by 15 over 105 divided by 15, which is 4/7, which is our desired answer. So that's the way this works. We just keep beating it down until with smaller and smaller arguments until we get something with 0, in which case the answer is something. Okay, one more example, then we're going to look at the code. So let's say we want to reduce 12 divided by 28. So we take the Euclid of 12 and 28, Euclid number of 12 and 28, which is the Euclid number of 28 and 12. We want to reverse that, which is the Euclid number of 12 and 4. So 28 is equal to 2 times 12 plus 4. So this is the Euclid number of 12 and 4. Well, 12 is a multiple of 4. So this is the Euclid number of 4 and 0. So the answer is 4. So when we get 12 divided by 28, we do 12 divided by 4 over 28 divided by 4, and so we would store this as 3/7. Okay, let me give you a preview of the star argument, which is the idea that any common divisor of two numbers must divide their Euclid number. Okay, so first of all, it's clear from the way that we've set this up that the Euclid number of A and B is a common divisor. Because, but it's just obvious from the way we've set it up. It's kind of, at some point, you just have to say, yes, it's obvious. And maybe pause the video, ponder, consider, try to figure out, go backwards and listen to what I said again, and try to convince yourself that it makes sense. So in the next video, this is what we're going to talk about in more detail. What we do is we basically, so here were our steps. This is sort of the more normal way of laying it out. 105 is equal to 1 times 60 plus 45. 60 is equal to 1 times 45 plus 15. 45 is 3 times 15 plus 0, and this was our GCD. What we can do is kind of run this algorithm in reverse. So we rewrite the second equation. So these were equations 1, 2, and 3. So 2 prime, we rewrite 2. We get 15 is equal to 60 minus 1 times 45. And if we rewrite 1 prime, we get 45 is equal to 105 minus 1 times 60. So 2 double prime, if we rewrite equation 2 by substituting the right-hand side of equation 1 prime. God damn it, you know what I mean. So 15 is equal to 60 minus 1 times, well, we substitute in this expression for 45. Let me undo. So we get 15 is equal to 60 minus 1 times 105 minus 1 times 60. And so 15, which is our Euclid number, or our GCD, is equal to minus 1 times 105 plus 2 times 60. So we get 1 times 60 minus 1 times 60, which is 2 times 60. So generally, you can always write the Euclid number of A and B as an integer-weighted sum or an integer linear combination of A and B. This fact is called the fundamental theorem of arithmetic. The Euclid number of A and B is a common divisor of A and B, just from the way we've set it up. By the fundamental theorem of arithmetic, any integer that divides both A and B, so any integer that divides both the right-hand side of equation 2 triple prime, must also divide the left-hand side. So any integer that divides A and B also divides the Euclid number. So it's sort of obvious from the way we've set it up. It is kind of obvious if you think about it, if you make a bounding argument. So the Euclid number is a lower bound of A and B, and the way we've set it up, it's also a upper bound of the lower bounds of A and B. But this fundamental theorem of arithmetic argument where you actually write 15 as something times 105 plus something times 60, then that argument is a lot more airtight because it's constructive, and we want to write out explicit procedures for coming up with these two numbers, which we can, because all we have to do is take what we're doing now and run it in reverse, but that's a little bit harder to do. We'll see, because when we do the Euclidean algorithm, the way we do it, we discard the quotients, but anyway. And so for this, you actually do have to pay attention to these quotients, which I told you were unimportant. They're important for coming up with these coefficients here, or the weights, whatever I called them. Anyway, so, but that's something we're going to do next time. Let's look at some code. I'm going to take a break, but look at some code. Welcome back. So, told you we're going to look at code. We're going to look at Erlang and Rust. We're going to look at Erlang first, and then look at some Rust and compare it to Erlang. So I have two modules here. So the way Erlang works is, let's just look at this module. Z is the standard mathematical notation for integers. And so this is, I think I mentioned QAnal is split into two subfields, XAnal, which means exact analysis, and preanal, which means precise analysis. So XAnal means that you can pin it down exactly, and preanal means that there's some notion of precision. So when we're talking about integers, this is exact, and then later on we're going to build a linear algebra library, which will be matrices, which will be QX under M. But first we need to talk about rationals, then we'll talk about, or we'll talk about integers, and then we'll talk about rationals, and then we'll talk about matrices. But let's talk about integers for a moment. So the way Erlang works, I mentioned there's modules. Each module exports functions. You have to list you can tell it to export all functions. But anyway, functions in Erlang are characterized by their name and their arity. Erlang's a dynamically typed language. It doesn't really have a type system. We'll learn more. It kind of has a type system, but not really. You can do type aliases like this. And the way the type system works, there's a static analysis tool called divisor, which will check, basically you give it information about, you give it type information, and what it will do is find cases where you've made a call that where you've, the function says it takes integers and you send it a string. It will catch that type. It will catch really unambiguous violations of the types, but there's not types are not really native to the Erlang runtime. It's kind of confusing. We'll see how it works as we go along. But anyway, as far as the Erlang runtime is concerned, their functions have a name and an arity. Arity means the number of arguments it takes, and all we care about right now is GCD2. These other two we'll get to. GCD1, remember how we talked about how, I don't have the notes pulled up right now. Let me do that actually, my paint. Open recent, might take a minute. So remember how we talked about how the GCD was sort of the least up or greatest lower bound of two integers in this divisibility graph? Well, the concept of greatest lower bound, there's nothing about two integers that's unique to the greatest lower bound concept. We could just as easily have a greatest lower bound of 5 integers or of 1 integer, which is actually how which is really actually how the Euclidean algorithm works. Is it says the greatest lower bound of 60 and 105, it reduces it. If we go down here, it will reduce the greatest lower bound of 60 and 105, and it'll say, just do a sequence of operations and say, that's the greatest lower bound between 15 and 0, or in other words, the greatest lower bound of 15. So we can just as easily do, let's say, the greatest lower bound of 5 integers, or 10 integers, or 50 integers. It doesn't matter. So that's why we can just as easily do the GCD of a list of integers, but we'll get to how that works in a little minute. Or probably not today, because I want to talk about something else. So remember our pseudocode procedure. Maybe I should put these two on the same screen. Can I do that? Okay. Remember how, so here's our basic pseudocode. So first thing we were going to do, take the Euclid number of a and b and say, well, we want both arguments to be non-negative. So that's all that GCD does for now. It sends it, says we want to take the absolute value of both arguments and pass the buck to this function GCD abs. So let's find this. GCD abs takes two non-negative integers and returns a non-negative integer. Then it does this. If x is less than or equal to, or if x is less than y, flip the arguments, send it to GCD plus. If x is greater than or equal to y, send it to GCD plus. So let's look at GCD plus. So GCD plus, let's see, did I write down anywhere explicitly how GCD plus works? Okay, well, there's just two cases. So GCD plus, let's actually just make it big. So GCD plus, so here we get to assume that the arguments are non-negative and they are in the correct order. So GCD plus of anything with 0, of x with 0 is x, and if x is greater than or equal to y, we actually don't need this check here, but it's kind of, in Erlang clarity, it's always good to like state assumptions like this. And we'll see that that's kind of fits in well with the way that you write code in Erlang, is stating assumptions very clearly. And it kind of makes the code easier to read. But anyway, I kind of wrote out the logic in a comment here. So x might be equal to y here, in which case modulo xy is equal to 0. So if you imagine GCD of 15 and 15, well, if you remember our procedure, that will just quickly degenerate into GCD of 15 and 0, in which case it'll be 15. So, right. X is equal to q times y plus r. Well, this is just the logic we did before. So q would be the quotient of x and y, and r is the remainder. R is x minus qy, and r is between, or is greater than or equal to 0 and strictly less than y. And remember, x is bigger than or equal to y here. Therefore, any common divisor of x and y, such as the GCD, also divides r. Therefore, the GCD of x and y is the GCD of y and r is modulo xy. So then we just call GCD plus of y modulo xy. So we just pass the buck until we eventually get to the sort of bottom case, which is GCD plus of x and 0, in which case we return x. Okay, this is the entire GCD logic right here. This is the heart of it, which is 4 lines of code is the heart of it. And then there's this sort of extraneous stuff up here, which is making sure the arguments are in the correct order, and then there's a modulo function, and we'll get to why I wrote that in a moment. Or, yeah, I can explain that. The modulo function, the heart of it doesn't really matter all that much for what we're doing. But so, literally it's make sure both arguments are non-negative. I go down here. Not GCD accum. Make sure that the arguments are in the correct order. Then GCD plus, just keep calling itself until you get to the bottom case, in which case the answer is obvious. Okay. Again, this is sort of like, it's the general pattern. You take a bunch of equivalent problems and you reduce them down to a very simple problem that you've already solved. Right. Take equivalent problems, convert them all into a problem you've already solved. So right, that was the general principle from last time. How did I phrase it? I think I liked the way I phrased it. Where did I put it? Right. Equivalent things have identical representations, or equivalently, equivalent problems have identical solutions, or I guess generalize the principle. And the strategy, pick one version of the problem that's the simplest version, solve it, and then convert all the equivalent problems to the already solved problem. That's what we're doing. Well, that's what we're doing here. We're converting all of these problems to our already solved problem, and we further convert this problem down into a trivial problem. So we convert E of 10560 to the trivial problem iteratively of E of 150. Okay. So it's just recursion. It's very, very simple. Okay. And then I want to just show you the code for, we'll talk more about, so let me actually split this window. And let's go up here. So there's a lot of function. This is all of the rational arithmetic in here. But let's. Oh, I wanted to show you actually that modulo function, just so that there's no confusion about what that's doing. And I can actually show you the GCD accum thing. That's not hard. Modulo. So there's this annoying thing. Let me show you. Let me make this go away. Okay, let me open Python, and let me open Erlang. Okay. In Python, if I do -3 remainder 4, that's 1. In Erlang, -3 remainder 4 is -3. And so I like the Python behavior more, where it always returns. Remember, we wanted to assume that R was between 0 and Y. And so this modulo behavior just kind of fixes that so that it's a little bit simpler. Okay, so for simplicity and obviously correct behavior, here we are. So, right, this is this is like the remainder operator, except this always returns a result within 0 and B. For simplicity and obviously correct behavior, B must be strictly positive. I actually think this doesn't. We could reduce modulo AB when 0 is, well, B can never be 0. You can never divide by 0. But if B was negative, we could just, actually, how's that supposed to work? Let me just try this. Let's do 3 mod 4 and 3 mod minus 4. Okay, that's really confusing. Let's just forget about that. Okay, it's really obvious what it's supposed to do if B is positive, and then when B is negative, it's a little bit confusing. And so this is a thing in Erlang, you code for the positive case, and then the cases that you don't expect, you crash on those. And that's kind of counterintuitive if you come from another language, with this idea that if everything isn't perfect, you crash. That's a standard operating procedure in Erlang, and that's actually somehow makes your code more robust. But it's kind of confusing. We'll see how that works. But anyway, basically, if so, B has to be strictly positive. So we do A remainder B, and I want to go back here. So if we did -3 remainder 4, what we want that answer to be 1. So if we take that and add 4, then we get the correct answer. And this is just generally true. So if we take A remainder B, and A happens to be less than 0, yeah, maybe we should case split. I don't know. There's probably a more efficient way to write this. But if -B is less than A remainder B and is also less than 0, this will happen when A is less than 0, return A remainder B plus B, which is just what we did over here, -3 remainder 4 plus 4. And if A remainder B is between 0 and B, then we would just return A remainder B. So we create two variables, negative remainder, which is when the remainder is negative, and positive remainder is when the remainder is positive. So -1 times B is less than A remainder B, and also A remainder B is less than 0. 0 is less than or equal to A remainder B, and also A remainder B is less than B. Okay. I always prefer writing my inequalities such that they match the number line. So that way you don't have to do flip. I always mess up signs and like having to transpose things in my head. And so if I don't have to do that, that's always better. So if we have negative remainder, so this is a Boolean, this will be true, false. This is a Boolean, this will be true, false. If we have a negative remainder, we return this is, by the way, just a general thing in functional languages, is the return value is always the last value in the... Every statement returns a value, and then the last value that's created in the function will be what it returns. So you can imagine putting return in front of here, but anyway. If it's a negative remainder, A remainder B plus B. If it's a positive remainder, just A remainder B, and that's it. Okay, let's look at the Q function. So first of all, what is a Q? A Q is a... Oh, I actually wanted to... Yeah, we can get to that in a minute. So what is a Q? A Q is a tagged tuple. So it takes... So Z is an integer, ZP is a positive integer. Remember that we decided that the bottom of the fraction has to be strictly positive. So what is this Q thing? Erlang has this idea called atoms, ATOM, and this is a feature that is really nice. Erlang has like all these tiny little features that are really, really nice that on their individually seem like, oh, that's really nice, and then you kind of have a language that has all of these nice, really little features. So one of them is called atoms. So lowercase, so variables, or what are they called, patterns. Erlang doesn't have variables because they can't vary. But patterns begin with capital letters and atoms begin with lowercase letters. And what the atom Q means is it means Q and it means nothing else. So let's go over here. Q is, you can't do Q is equal to 1. It'll say, no, the left hand, you can do Q, oops, Q is equal to 1. That's perfectly fine. But then on the next line, if you say Q is equal to 2, it crashes. It'll go, no, you said Q is equal to 1. But the atom Q is equal to, it's a naked value. It doesn't mean anything beyond Q. If I write potato, it means potato. It doesn't, it's stored as an integer, but like under the hood it's an integer, obviously. But this is the right way to do C-type constants. So you know how if you're programming in C, you know, you'll define all of these insane constants as integers, and in Erlang instead you just use atoms, and then if you want the atom potato, you call it potato. Anyway, so I can do potato equals potato, and it says yes, that's correct. But I can't do potato equals Q. It says no, potato is potato and Q is Q. What are you talking about? And it'll crash. Okay, so Q. We take two integers and form their quotient. Never allowed to divide by 0, so if we try to divide by 0, we crash. Q of n1, we don't need to reduce the fraction. At that point, it's Q n1. We technically don't need this case because but it's sort of a shortcut. Q of the top and bottom, if the bottom is negative, this is to fix the sign convention, saying call Q again, but flip the sign, multiply both top and bottom by -1. All right, Q of top and bottom. When the bottom is less than 0, or bottom is positive, and both the top and bottom are integers, then we take the GCD of the top and bottom, form the quotient of Q divided by the GCD, and the bottom divided by the top divided by the GCD, and the bottom divided by the GCD. That's it. And I also wanted to point out this square function, talk about how we square a rational. Oh, we just multiply it by itself. And how do we do multiplication of a rational by itself? Yeah, to multiply a to, let me just show you. Let me just plug it in. Micro USB is the devil. So if we have A over B times X over, not X, let's do C over D, this is equal to A times C over B times D. That's it. You just multiply the top of the fraction and multiply the bottom. And then the idea in Q, every time it constructs a rational, it calls this Q function. And so multiply times, we unwrap it, so we get a rational QTLBL and QTRBR. Take the quotient of TL times TR and TRBL times BR, and so when we square, we just multiply something by itself. Okay, and I just wanted, and then I have a little script here. Let me unplug the drawing pad. And let's go up and show you the tests. Okay. So first let's run some GCD. This is called an E script, which is, it's an Erlang script. Okay. So it exports a single function called main. So GCD test runs it on 4 test cases. GCD test, all it does is it prints GCD of such and such equals the result. That's it. Okay, so let's run tests.url. Uh-oh. Oh, it's just a warning of unused functions. But anyway, the GCD of 60 and 22 is 2. The GCD of 11 and 22 is 11. GCD of 2 and 4 is 2. The GCD of minus 60 and 105 is 15. Okay, cool. Now, let's look at the Q-tests. I should have interspersed them. Here, let me do that, actually. And then I want to show you. And actually, let me make a GCD test of 60 and 107. Okay, so the GCD of 60 and 22 is 2. And so when we take the quotient of 60 and 22, it has the effect of dividing both the top and the bottom of the fraction by 2. So 30 is 60 divided by 2. 22 is, or 11 is 22 divided by 2. The GCD of 11 and 22 is 11, so the quotient of 11 divided by 22 is 1/2. GCD of 2 and 4 is 2. The quotient of 2 and 4 is the quotient of 1 and 2, which is the outcome of dividing both arguments by the GCD. GCD of minus 60 and 105 is 15, so the quotient of minus 60 and 105 is minus 4/7. The GCD of 60 and 107 is 1. And the quotient of minus 60 and 107 is minus 60 and 107. Awesome. Okay, let's talk. There, that's it. Oh, and I wanted to just show you the squaring thing works the way you expect. Let me just comment these out. Okay. GCD of minus 60 and 107 is 1. The quotient of minus 60 and 107 is minus 60 and 107. And then I assume 107 squared is 1,001 or 11,449. But minus 60 and 107, you square that and you get 3,600 over 11449, I assume. Okay. Now, the reason I'm doing the square thing, you'll see in a moment. So let's switch over to Rust. Okay. First thing I'm going to show you is GCD implemented in a way that's a very functional style. So Rust supports both functional styles and imperative styles of programming. And I chose Rust just because it's a pretty simple language that there's very little weirdness to the language, as opposed to, you know, C or Python or something where there's all sorts of weird shit that can happen. So let's actually split it. Hopefully this is big enough that you can see it. So here I mostly just wrote my Erlang program. That's so annoying. Okay. So here I mostly just wrote my Erlang program, but in Rust. So GCD of A, which is a 64-bit signed integer, and B, which is a 64-bit signed integer, that's what I64 means, returns an I64. So let absolute value of A, which is an I64, which is a 64-bit integer, be the absolute value of A, and apparently Rust doesn't have a built-in absolute value, or it probably doesn't. I'm not a Rust person, so I just wrote one by hand. The absolute value of X, it works exactly the way you think it is. If X is greater than or equal to 0, returns X, otherwise multiply it by -1. There. And then, right. Pass the buck to GCD abs. GCD abs, it works exactly the same as our Erlang program. So, GCD abs of A and B. So make sure the functions, the inputs to GCD plus are in the correct order. The way I implemented this was I made a function called bigger. So the way this works, it returns the bigger number. So if A is greater than or equal to B, so of two I64s, if A is greater than or equal to B, return A, otherwise return B. And then smaller Well, this, let me just write out the logic of this. I gotta plug the fucking micro USB. It's just, God, who invented that? Okay, so if A is less than B, then it's also true if we multiply both sides of this by -1, then minus B will be less than minus A. So if we want to find the smaller number of A and B, well, what we can do is find the bigger number of minus B and minus A, and then return minus that. That was the logic I had. And I could just as easily copy the logic, but this just seemed simpler, at least to me. So return the smaller number, -1 times bigger of -1 times A and -1 times B. Okay, so that's how bigger and smaller work, and then return GCD plus, pass the buck to GCD plus of bigger and smaller. GCD plus. So we now get to assume both inputs are non-negative and A is greater than or equal to B. If B equals 0, we return A. Otherwise, we set R equal to the remainder of A and B, return GCD of B and R. So it, ooh, actually this should be GCD under plus, but it doesn't matter. Okay. So GCD plus of B and R. That should be the way it works. Okay, and so we can, and then I have a main function for testing this, so let mute means mutable A. So if A is 60 and 22, this works the way our test script in Erlang wrote. So let me do, what is it, rust c gcd functional.rs functional, and if we compare that to what we got in Erlang, it looks like, now I wish I hadn't, here let me just undo a bunch of times, and let me comment these out, just so that we, so, and just compare it, we got 2, 11, 2, 15, and in Rust we get 2, 11, 2, 15. So at least our implementations agree on these little examples. Okay, now let's look at GCD implemented in a more imperative style. And this is, I think, this is really what I wanted to show, was the functional style versus the imperative style. Okay, so we have abs, bigger and smaller, which are the same as before. So GCD, we don't want, here it is in imperative style. GCD of A and B don't want the headache of negative numbers. So let abs A, which is an I64, be the absolute value of A, and absolute value of B be that. Okay. Now we have to define mutability. Let mute bigger, I64 is the bigger number, and smaller be the smaller number, and let rem be the remainder. And what we're going to do is we're just going to keep doing remainders until we get a remainder of 0. So rem is bigger percent smaller, bigger is equal to smaller, so, and smaller equals remainder, and then return bigger. And I'll let you figure out the logic of why that works. But it's I think the recursion logic is a lot cleaner. So let's just compare. Shut up. Yeah, I just read only is fine. Jesus Christ, Vim. Okay, I want you to compare. If I delete the comments here, let me just delete the comments. Shut up, Vim. You, Jesus Christ. Okay, 4 lines of code for our logic over here, which is essential. Here, I guess, the essential logic over here is also basically 4 lines of code. I think the functional style is a lot clearer. It's a lot more obvious what's going on. Here, you have to keep, juggling this state machine in your head, and it's much easier to debug functional code. That's the point. So anyway, so what else did I want to show you in Rust? Oh, and we can also do our test here. we can do gcd.rs, test this, and run it. 2, 11, 2, 15, same sequence that we got before. So works in this little example. Now what I wanted to show you, first of all, I implemented the same thing with 8-bit integers, and I'm going to show you why. So first of all, I made this one public just so that it would get exported, and I just copied the functional code and changed all instances of i64 to i8. And i8 is assigned 8-bit integer rather than a 64-bit integer. And this is to illustrate an issue that can come up when you're doing rational arithmetic. Okay. So we do all of this, same exact thing with 8-bit integers. I don't know. Oh, turn off that dumbass warning about unused main. That's what allow dead code is. So if we do this, these are all pretty small numbers. They all fit into 8-bit integers, but let's just do gcd8.rs. This is exactly GCD functional, but I changed everything to 8-bit integers. Okay, and if we do GCD8, same sequence as before. Okay. Now I also implemented the basic quotienting logic in Rust with 8-bit integers. Okay, and this is to show an issue that can come up with quotienting logic that Erlang just solves naturally. So, rational arithmetic half example in Rust, implemented with 8-bit integers just to show the issue. So, I don't know Rust super well. This is kind of like an import, and derived debug, so this is so we can print the Q struct easily, which is an equivalent to term formatting in Erlang. Apparently in Rust that you have to specify that you can make copies of things. So derive, clone, and copy. And so here's our data structure, Q, which is has a top fraction and a top and bottom of the fraction, which are both signed integers. The Q of the top and bottom returns a Q. This eliminates top and bottom of the fraction, reduces the fraction, and makes sure that negative fractions have the top integer be negative and the bottom integer be positive. So first of all, let's compare this to... oh boy, I have so many projects. Shut the fuck up. Jesus Christ. Okay. Here's our Erlang logic, which is... what? 12 lines of code, it seems like. Okay, so let's compare this. Now, granted, I have tons of comments here, because you have to do more comments in a... Anyway. So, Q of T and B. This eliminates common divisors between top and bottom. It reduces the fraction and makes sure that the negative fractions of the top integer be negative and the bottom integer be positive. Okay, so if B is equal to 0, we crash. And we crash with the message, you can't divide by 0, you asshole. So this line of code over here is basically the same as over here. If the bottom of the fraction is 1, we don't need to do that GCD stuff. Nothing would break if we didn't explicitly check this case. That's important. But it's kind of good for clarity, I suppose. The reason it wouldn't break, because the GCD of anything is 1 with 1. And so the code in the else block would just divide the top and bottom of the fraction by 1, which does nothing. If B is negative, then we do a re-entry call with -1 times T and -1 times B, so it's this logic. So I just more or less copied the logic from Erlang over into Rust. Okay, else. At this point, we can assume that the bottom of the fraction is strictly positive, divide both the top and bottom by the GCD to reduce, so let GCD, so this is this, GCD of top and bottom. The new top is T divided by GCD. The new bottom is bottom divided by GCD. Return new top and new bottom put into the Q data structure. Okay, and then I also wrote this square function, which just takes... So you have to kind of unpeel the logic inside of here, which is annoying. You can't do a lot of matching, I guess. Rust does have pattern matching, but it's kind of clunky. So T and B, I mean, Rust is what it is. I actually kind of like the language, but anyway. So, square a rational, which is a Q, we return another rational. T is an I8, B is an I8, which is the top and bottom. These are fields in the record, rat.top and rat.bot. Return a new Q, which is top, which is T times T, and bot, which is B times B. All right, so main, we define mutable A and B, which are 8-bit integers. Okay, so 60 divided by 122, 11 divided by 22, 2 divided by 4, minus 60 divided by 105, and minus 60 divided by 107. Now let me go over here. Okay. Let me comment these out, and we'll just do our Q tests over here. Okay, we get 30 elevenths, 1/2, minus 4 sevenths, and minus 60 over 107. Okay. Okay. I am actually going to comment this out for a moment, just because this will show what the issue is, okay? So let's just check it. Rust C Q.rs. And we get 30 elevenths, 1/2, minus 4 sevenths, and minus 60 over 107. And if we look over in Erlang, 30 elevenths, 1/2, minus 4 sevenths, and minus 60 over 107. I haven't bothered defining pretty printers. You can do that pretty easily in both languages. Anyway, let's try squaring. Okay. And this will show what the issue is. So we define rat, which is a quotient, and rat squared, which is another quotient. So rat is, I used minus 60 over 107 as an example, and rat squared squares it, and then it'll print rat is equal to this, and rat squared is equal to this. So let me show you what happens in QAnal when we do this. So let's just do this. So minus 60 over 107 is that, and you square it, you get that. Okay, let's try it in Rust. Now, I purposely chose 8-bit integers, and you can probably predict what's going to happen. So let's compile q.rs and run /q. Uh-oh, it crashed. So what happened? Well, an 8-bit integer has a range from minus 128 to 127. And if we go back over here, you know what, it'll be easier. Anyway, this is 3600 over 11,449, sorry, which is within 64-bit integers, well within the range. But with 8-bit integers, that's out of range. And so what happens if you have fixed width integers? Erlang has variable width integers, are called big nums, which is why Erlang is nice for this. You get what's called integer underflow or integer overflow. Now in C, this is a major source of bugs. Rust actually compiles by default with overflow checks, which will crash if you have overflow. But you can turn overflow checks off. I wrote down how to do that. And if we do that again, now, so if we did this in C, it would just give us a wrong answer because computers actually just do modular arithmetic. So what it would do is, let me split this. So 3600 remainder 256, so that's the biggest 8-bit integer, is 16. And then what was it? It was 11449, remainder 256 is 185, but remember these are signed integers, so 185 minus 256, that's minus 71. And so somehow this gets that it's, number one, we have a signed integer on the bottom, which was forbidden. So Rust happens to catch overflow and underflow, but it'll crash. In Erlang, it just uses big nums. So if you get beyond whatever a 64-bit signed integer, it'll just it will what will it do? If you get beyond a 60, oh, it'll just start using bigger integers. So that's a reason that Erlang is nice, because it has big number arithmetic built in, because it sort of assumes that if you start getting really big numbers, then you probably don't want this weird modular arithmetic behavior. If you want it, you'll code it in explicitly. Anyway, that's all I have to say. I wanted to compare what I really wanted to compare was sort of the sawtooth-y imperative style of Rust to the more compressed functional style of Erlang, and I personally think the Erlang is a lot easier to read. It maybe takes some getting used to, but definitely, it's certainly easier to debug, and I think it's also easier to read. It's easier to debug because it's easier to read. Anyway, that's all I have to say for now. I will see you in the next video. What are we going to be talking about the next video? Probably the rest of rational arithmetic. So times, 0, square, 1 over, the pretty formatter, all that, how to subtract. That's all I have to say for now, though. Thank you. Goodbye.